Hello, folks, and welcome. I'm Dansha Balsara. I'm your instructor for Physics 10320. And what I've decided to do is basically produce a sequence of videos. I'll try to produce them as much as I can. I can't guarantee that I'll produce a video for every lecture, but I'll try to produce as much of them as I can. And these are actually designed to help you guys to master the subject. And what are we actually seeking for in any educational situation? What we're actually looking for is to produce a situation where the student has true mastery of the subject. So that's the point that we're trying to accomplish, namely, the student has true mastery of the subject. And mastery comes to different people in different ways. For example, there might be somebody who can master a subject just with one or two recitations. There might be another person who might need three or four recitations of the subject before she or he can master the subject. But it really doesn't matter how you achieve mastery. What actually matters when you're trying to accomplish true learning is the fact that mastery should be achieved by the student. And therefore, the important thing out here when achieving mastery is the importance of repetition. There's a lot of educational research these days which shows that with repetition, everyone can master a subject, even if it is a difficult subject. And maybe you might think of physics as being difficult, but these lectures are designed to essentially simplify the whole process of mastering the subject. Okay? So with this understanding, we should understand also how this mastery is to be achieved. Now, one secret I will let you in on is that basically the best way to learn a subject is with the help of a professor or a teacher right in front of you explaining the subject to you. Unless you engage with the subject in this fashion, basically thinking about the subject and thinking about how the subject was put together, you're not going to master the subject as such. So the important thing is that in-class engagement is truly crucial for achieving true learning. Okay, so please do come to class, and if you come to class, you will learn, and these videos will essentially buffer you up. They will supply you with the additional extra help that is needed to actually master the class. However, I have to be honest with you and tell you that if you don't come to class regularly, then just downloading the videos and watching them at home, or maybe downloading them and watching them en masse before the midterm exams, is not going to help you. So with that, we are essentially going to go ahead and say that there's an optimal strategy for achieving mastery. And that strategy consists of first reviewing the material before you come to class, then participate fully inside the classroom. The classroom is intended to be highly participatory from the viewpoint of the students. And then when you have a chance, go back home and review each and everything that was taught in class. That will help you to seal in the knowledge. And that strategy, that three-part strategy, will also help you with reviewing for tutorials, tests, exams, and so on and so forth. So with that, let's go ahead, and now that we've established the goals and expectations, let's go ahead and dive into the chapter that we're about to study. This is the first chapter that we're going to study in this course. It's associated with electric charge and electric field. So what is this course consisting of? This course is essentially based on understanding electricity and magnetism and how it plays a role in the modern technology base that we're living in the midst of. For example, each of you all most likely carries a cell phone, and that cell phone basically uses electromagnetic radiation to do a whole bunch of things for you. It uses the electromagnetic radiation to communicate with the cell tower. Likewise, it gets GPS information from satellites and processes that to tell you where you are and how you need to move in order to go from one location to another, and so on and so forth. So electromagnetic effects play an important role in just about all the modern devices that we interact with. Also, as you would imagine, in order to sustain our level of technology evolution, what we need is to keep evolving novel technologies based on novel materials. And in fact, the forces that hold atoms and molecules and various solids and liquids and gases together are in fact all based on electromagnetic forces. So electromagnetic phenomena are extremely important for modern devices. They're also extremely important for understanding new materials and their uses in technology. And with that extremely utilitarian uh, understanding, let's go ahead and focus on how electric charges are made of. So we essentially understand that we have two different types of charges. We can have negative charges, which are basically carried by electrons in our workaday world that we live in. And we can have positive charges, which are basically carried by protons in the workaday world that we live in. So if you think about it, a typical atom will consist of essentially three fundamental building blocks. There'll be protons in the nucleus, which are positively charged. For example, here I'm drawing two protons, which are positively charged. And to compensate for that, there are also neutrons, which are electrically neutral. And to preserve the neutrality of the charge of the atom, there are electrons that are in an orbit around it. So these are the electrons which are negatively charged. And the interesting thing is that these particles, of course, they're divisible in an atomic smasher, but other than that, they're basically, for our typical science and technology uses, we think of these as not divisible because essentially you can't have half of an electron. Likewise, you can't have half of a proton unless there's other considerations involving particle physics. So short of those considerations, we will essentially say that we want to think, in at least for the limited reasons of this course, we want to think of these particles as indivisible. And therefore, this basically introduces us to the notion of charge conservation, which basically says that these particles are fundamentally preserved, and what happens is that you can essentially trade them from one object to the other. Now, the easiest way of trading charges from one object to the other is basically to resort to friction, namely to try and build up static electricity. For example, on a cold winter's morning, you might actually find that combing your hair causes your hair to try and stick to the comb. Why is that so? It's so because your comb wants to acquire one type of charge, your hair has a predisposition to acquire an opposite type of charge, and the two charges do not neutralize because the air is so dry that there's no medium available, namely there's no water vapor available to kind of conduct the two charges and make them neutralize. So we actually go ahead and ask, what is one of the easiest ways of producing uh, an imbalance of charge? So uh, say we started with a glass rod and we rubbed it with a silk cloth as is shown out here. Then because of the way these materials are made, glass has a predisposition to donate away its electrons. Silk has a predisposition to actually acquire its electrons, and therefore by using friction we can actually have a situation where a glass rod can acquire an excess of positive charge, which is equivalent to a deficit of electrons. Of course, the charges don't go anywhere. The electrons are basically still resident on the silk. You can also have a situation where you have a rubber rod, which is rubbed with a uh, piece of fur, and then you can have a negative net charge developing on the rubber rod. With this understanding, we're now ready to do some simple experiments and we can essentially bring a positively charged glass rod next to a negatively charged rubber rod, and we will find immediately that the two rods will attract each other, and that tells us that opposite charges begin to attract one another. If we do the same experiment with two negatively charged rubber rods, we will actually see that like charges repel each other, and that gives us our first insight about static electricity and how to work with it, and we might even do such similar demonstrations inside class. So with that, we essentially have understood that you can only have discrete packages of charges jumping from one object to the other. This is known as quantization. A quantum requires to a package or a single unit. And essentially, when you have charges jumping from one object to another, you can only acquire these charges in discrete integer multiples of the fundamental unit of charge, which is the charge available on the electron or the proton. Now, this fundamental unit of charge is actually a very small unit of charge. Our units of charge in MKS units are called coulombs, and an electron, an individual electron, only has 1.6 times 10 raised to minus 19 coulombs. So you essentially understand that this is a very small unit of charge. And if you take a typical charge that you might actually transfer across an electronic device, namely a charge of around 60 microcoulombs, then you realize that the amount of electrons, the number of electrons that you have to transfer in order to transfer that much charge is really quite phenomenal and is shown to you out here. So you have to transfer about 3.75 times 10 raised to 14 electrons to make up that much small amount of charge that we're talking about, which basically gives us the idea that even though charges are transferred in discrete units, we can actually think of charges as being part of a continuum, and that gives us our understanding that, okay, truly charges are quantized, but in practice, we can think of them as being a continuum. With that said, we already got introduced to the notion of micro and milli, and so we will actually go ahead and lay out some scales, because these scales actually play an important role, especially when you're doing problem solving. So what does kilo represent? Typically, we think of kilograms, which basically corresponds to 10 raised to 3 grams. So kilo represents 10 raised to 3. If you think about the cost of an F-16 aircraft, it costs about $20 million, and you could actually say that an F-16 aircraft costs about 20 megabucks. So mega stands for 10 raised to 6. If you ask what is the speed of your typical Intel CPU that resides in your computer, it typically does 10 raised to 9 or some multiple thereof of float point operations per second in order to give you the seamless experience that you need. And we can therefore say that it does about a gigaflop or a few gigaflops of float point operations per second. So FLOPS stands for float point operations per second. Those of you all who are computer scientists already know that. A long time ago, I went ahead and tallied up the national debt, and it seemed to me like it was 10 raised to 12 dollars, which corresponds to terabucks, and I haven't gone ahead and thought about it since. Now, if we go down in scale, we actually come to the notion of a millimeter. A millimeter is the smallest unit that you can probably see on a foot ruler. And a milli refers to 10 raised to minus 3. So a millimeter is about 10 raised to minus 3 of a meter. So milli stands for 10 raised to minus 3. If you think about the size of a biological cell, it is 10 raised to minus 6 of a meter, which we therefore call a micrometer, and therefore it stands to reason that you use microscopes to actually visualize a biological cell. If you ask what is smaller than that, you come to the nanoscale, which actually refers to a length of 10 raised to minus 9 meters. And on that length of scale, the discreteness of the atoms begins to show through to you. And with that, we essentially understand how to get our symbols and what their value implies. And therefore, let's go ahead and move on to the next section. So when we think about the typical workaday materials, the workaday objects, the solids around us, we essentially think of them as being made up of metals and nonmetals. Now, if you think about metals, you will realize that all of them typically tend to be very shiny. For example, copper is very shiny, aluminum is very shiny, silver and gold and iron are also very shiny, and they're shiny for a very specific reason. They're shiny because what happens is that when atoms of copper or iron or silver come together to form a solid piece of copper or iron or silver, they actually do something quite funny. Namely, there's a certain fraction of the electrons that are bound to an atom which find it energetically preferable to actually go ahead and release their moorings to each individual atom and rather belong collectively to the entire piece of copper or iron or silver that we're talking about. You can think of it as somebody in your dorm who is extraordinarily sociable. That person just doesn't stay in his room, but rather flits around from one room to the other, chatting with this guy, that guy, and the other guy. And therefore, that's a good analogy for the electrons inside a conductor. Now, what that does is it actually gives conductors their unique properties. One of the properties is that a conductor is actually very good at conducting electricity. Why is that so? It is so because the electrons inside a conductor can freely go from one end of the conductor to the other, and therefore they can carry electric charge along the conductor. That is actually why copper is used for the electrical wires that bring electricity to you. Another consideration is that because these electrons are free to move around, anytime you have any sort of electromagnetic radiation falling on a piece of copper or a piece of silver or whatever, the electrons are set into copious oscillation, which actually causes the electromagnetic radiation to be reflected off of the copper or silver or so on and so forth. This is actually why metals tend to be very shiny. They basically reflect back any electromagnetic radiation that falls on them. So this explains to us many aspects of metals, and it also explains to us why metals play a very important role in our electricity and magnetism based technological society. Now, if you have a bare piece of copper and you run an electric current through that copper wire, you're definitely going to go ahead and get electrocuted. So insulators also play a very important role because in insulators, the electrons are basically bound to the atoms, and therefore electrons cannot move freely through an insulator. So while electrons were able to move freely through a conductor, electrons do not move freely through an insulator, and that is why uh, outside of any copper wire, you will find a sheath of plastic or rubber or whatever to basically insulate you from getting electrocuted by the current that is flowing inside the copper wire. Now you may well ask, are there any materials that sit between conductors and insulators? And indeed there are, because that class of materials is to some extent even more important in Silicon Valley than anything else. So you see that this whole notion of Silicon Valley is built around the fact that silicon and germanium have this property of being semiconductors. They're neither conductors nor are they insulators, but they can masquerade to some extent like conductors and insulators, and therefore they can be given very special electronic properties which make them extremely useful in electronic devices. So with those insights, we're essentially ready to move forward and ask how we can actually charge up a conducting object. So here you're shown essentially a conducting ball, and this conducting ball has, as it were, equal amounts of positive and negative charges, as you can see from the figure. So you can actually count up the number of positive charges and negative charges and see that this conducting ball is initially electrically neutral. Now, what do we do if we wanted to go ahead and charge it up? So we'll actually go ahead and try to do an analogous demonstration inside the classroom. But let's go ahead and see how we can actually go ahead and charge up this electric ball. I'm sorry, this conducting ball. So what we do first is we take a rod which is negatively charged and bring this rod close to our conducting sphere. What that does is it basically causes the positive charges to be strongly attracted towards the rod, and it also causes the negative charges, like this one, to be repelled away from the rod. So what we see is a situation where on the left side of our sphere, we built up an excess of positive charges, and on the right side of our sphere, we built up an excess of negative charges. So we have negative charges piled up on the far side of the sphere, the right side of the sphere, and then the next stage, what we do is we take a conducting wire like this one and connect that wire to the ground. Now, what the ground does, or the earth does, we say that a wire is grounded if it's connected to the ground. What the earth does, or the ground does, is that the earth is so big that it has an amazing excess of charges of any sort that you want. So in this case, you have lots of negative charges piled up on the far side, namely the right side of the sphere. I'm sorry. And if they're given a conductive pathway that connects them to the earth, what the negative charges want to do is they want to essentially conduct themselves away into the earth. So, if you allow for a passageway, namely a conducting wire that connects to the earth, these charges, these negative charges will dribble right into the earth, and then we will essentially have a situation like the one shown out here. So you still have the negatively charged rod next to the sphere, but what you've done now is you've taken away this conducting pathway. You've basically gone ahead and rubbed it off or erased it off or taken away the wire. And therefore, you have a situation now where you have built up a net positive charge on this conducting sphere. What you do in the last step is that you basically take this rod away, far, far away. And that's shown to you out here. And now what you've produced by a process of induction, namely a process of bringing something, inducing some changes, and then removing that same thing. In this case, the thing that did the induction was the negatively charged rod that we had in our story. What we have done is essentially produced a net positive charge on this conductor out here. So this is an example of charging by induction. And let's go ahead and now address this thought question. These are little questions, mostly conceptual, not requiring a ton of mathematics, which are peppered all through my lecture notes. And they essentially are designed to teach you the subject at a conceptual level. So please go ahead and read this question, and I will explain it in the next transparency with little drawings. So let's go ahead and now ask what happens in this situation. So we first start with a conducting metallic plate, which is in fact connected to the ground. Okay? Right now, the plate and the ground and everything else are neutral, but from far away, we're essentially taking this positive charge plus Q and we're bringing it close to the conducting plate. So in the next frame, we have a situation where we have this conducting plate. It is connected still to the ground, and we have this charge plus Q very close to it. Now, what will the charge plus Q want to do? If it has the facility to do so, it will try to attract negative charges to itself. But notice that because the plate is grounded, it is essentially connected to the earth, which is an infinite supplier or absorber of any sort of charge you wish. So now you have a situation where electrons from the Earth will gladly flow into this conducting plate and make it negatively charged. Okay? What we're showing in the third panel, which is this panel, which I don't have to draw, is that in this panel, we still have the same configuration, but there is actually a switch connecting the wire to the ground, and this switch in this third panel has been opened. So those negative charges were still resident because they're still wanting to stay attracted to the charge plus Q, but now any pathway for exchanging charge between the plate and the ground has been broken. Now, what happens is that we now take this charge Q far, far away. And then we ask what sort of charges are going to be left behind on this conducting plate. And in the fourth panel, of course, you can imagine that the charge Q has been taken far, far away. The switch is open, so there's no pathway between the plate and the ground. And this plate is left behind with an excess of negative charge on it. And so that's the answer to this question. So if you go scroll back by one transparency, you will find that the correct answer to the thought question is D, which says that it is negatively charged. Okay? So now let's move forward. And now let's go ahead and make our knowledge a little more quantitative. So up to now, we've only described in a qualitative way what is happening. Let's go ahead and make our knowledge more quantitative and understand why charges are attracted to each other. The reason anything moves in physics is because there are forces that make it move. And there are such forces that cause opposite charges to be attracted to each other and like charges to be repelled from each other. Now, if we go ahead and do a highly calibrated experiment as is shown in this torsional balance to the right, what happens in this torsional balance is that you can actually put one type of charge on the charge A, the sphere A out here, and you can put another charge on the sphere B out here and sneak it into this vessel using this hole. Now, this charge is perfectly balanced with this counterweight out here, and it is connected to this torsional fiber. So with this torsional fiber, by twisting the fiber, you can apply different amounts of torques and therefore different amount of forces to the charges. And therefore, you can go ahead and measure the force between charge A and charge B, whether it is attractive because the two charges are oppositely charged, or repulsive because the two charges are like charged. You will find that the force, if we write it as a scalar, of course the force is a vector, but the force is actually given by some proportionality constant times the product of one of the charges, which we'll call Q1, the other of the charges, which we'll call Q2, divided by the distance between the charges squared. So the force, the electric force, F sub E, is always directly proportional to the product of the two charges and inversely proportional to the square of the distance between the charges. This force law has a name, and that name is essentially Coulomb's law. So now let's go ahead and study Coulomb's law in more details. So we'll actually go ahead and understand why the structure of Coulomb's law allows us to deduce that like charges produce repulsion, unlike charges produce attraction, and essentially understanding how this force is oriented. So let's go ahead and study it mathematically. So we see that the force, the electric force as shown in this equation out here, and you should try to memorize such an equation, is actually given by In the numerator, the product of the two charges. In the denominator, the square of the distance between the two charges. But there is this proportionality constant. This proportionality constant is called Coulomb's constant, in honor of Coulomb, who discovered the Coulomb force law. And for our purposes, we would be just fine if you thought of this proportionality constant as being 9 times 10 raised to 9 in MKS units. Now, how do we get to this notion of the units of K? The answer is that force, which has units of Newton, in this case, the electric force, is equal to the Coulomb constant times Q1 times Q2 divided by the distance squared. And Q1, Q2 means the product of Q1 and Q2 has units of Coulomb squared. The distance squared has units of meters squared. And therefore, K actually has units of Newton meters squared, because you took this meter squared and brought it to the numerator out here, and you took this Coulomb squared and brought it to the denominator out here. So you have K having units of Newton meters squared divided by Coulomb squared, which is exactly what is shown to you out here. Okay? Now, later in the next chapter, we will also want to write K in terms of some other entity, and we will want to write K as 1 over 4 pi epsilon 0, where epsilon 0 has a special name. It is called the permittivity of free space. We will understand why epsilon 0 is an entity with some use to us. Okay, so with that, let's go ahead and just flash before you the amount of charge on an electron and proton and show that they're basically exactly equal and opposite. The masses of these objects is also shown to out here. And now let's go ahead and realize that so far we've just understood Coulomb's law provisionally, understood the scalar aspects of it, but now it behooves us to actually understand it more vectorially. So let's go ahead and, in true physics form, set up a coordinate system. This is x, this is y, and we can actually have a position vector, which I'll call r1 vector, which gives me the position to the charge q1. I can have a position vector, r2 vector, which gives me the position of the charge q2. Notice that these two charges are positive charges, therefore the forces between them are repulsive, and from symmetry you can imagine that the forces should act along the line joining the two charges. So F12 is indeed the force on charge 2 due to charge 1, and F21 is indeed the force on charge 1 due to charge 2. Okay? Notice that these two forces are equal and opposite, and they have to be because of Mr. Newton's third law, which says that forces essentially come in equal and opposite pairs. Now, in order to, we've already studied the scalar part of this force law, namely K times Q1 times Q2 divided by R squared. Now let's go ahead and study the vectorial aspect of this force law. So essentially, all forces are vectors, and therefore we have to write them in a vectorial form. And so R12 hat is actually this vector out here. It is a unit vector that connects charge 1 to charge 2. How do you obtain such a unit vector? The answer is very simple. We say that R12 hat, with the hat denoting the fact that it's a unit vector, namely a vector of length 1, is just equal to R2 vector minus R1 vector. Notice R2 vector and R2 vector minus R1 vector is just this total vector that connects charge 1 to charge 2. But that's not a unit vector. So we make it a unit vector by dividing it out by its length. So we obtain R2 vector minus R1 vector in the denominator. In the denominator, we just multiply it by a scalar, which is the length of that vector. That is, in fact, this distance r, and that is how we obtain a unit vector that connects or that points in the direction of charge 1 to charge 2. Notice that very many interesting things fall in place. We see that this unit vector r12 hat is actually pointed in this direction as I'm showing right now, which is also the direction in which f12 vector is pointed. So it tells us that this choice is indeed correct, as long as q1 and q2 are both of the same sign. So therefore, we obtain the repulsive aspect of this force. Notice that the force acts vectorially along the line joining the two particles, and it is repulsive if the two particles have like sign, and attractive if the two particles have opposite sign. Now let's go ahead and see what happens if the two particles have opposite sign. If the two particles have opposite sign, then Q1 and Q2 will have opposite sign, and therefore their product will have opposite sign, which basically means that in front of R12 hat that you see in this equation, you actually have something with a negative sign, which causes this F12 vector and F21 vector to essentially flip directions. And that's how Coulomb's law arranges for like charges to be repulsive and unlike charges or opposite charges to be attractive. Now, what I've shown to you out here is actually a interesting compare and contrast that we can do with the force of gravity. So the force of gravity between two masses is also directly proportional to the product of the two masses and inversely proportional to the distance squared between the two masses. So we see that that aspect of the analogy is exact. Likewise, for Coulomb's law, we have Coulomb's constant. For Mr. Newton's law of gravity, we have Newton's constant. We also have this unit vector, which is common in the two forces. But notice that there are also interesting points of difference. All masses are always positive, and therefore F12, the force of gravity, by virtue of this negative sign, will always be an attractive force. On the other hand, charges can be positive or negative, and therefore Coulomb's law will allow for us to have either a positive force of attraction or either a force of repulsion between like charges or a force of attraction between unlike charges. So that's how Coulomb's law manages to produce both attraction and repulsion. With that, I'll go ahead and leave this next set of thought questions for you. We'll try and do them in class if possible, but I would urge you to realize that all of these thought questions are essentially hearkening back to some physical law or some physical insight that I have given you and I'm trying to reinforce in these thought questions. So please go ahead and think about it, and we'll address it in class. We will now go ahead and ask what we get from Coulomb's law in a more complicated situation. So Coulomb's law, as shown to you up to this point, pertains to the fact that it is a force between two point-like charges. Okay, so now what happens if you have a charge Q1 and you want to find the force on it due to not a single point charge Q2 or Q3 or Q4, but you have essentially out here an entire configuration of charges that are exerting a force on Q1. So there's Q2, Q3, and Q4, Q2 being positively charged, Q3 being negatively charged, Q4 being positively charged, which are all trying to exert forces on Q1. Superposition principle just tells you to think pairwise for each individual pair of charges, but it also tells you not to think of the self-force that you might have. So for Q1 and the forces on it, we basically ask, what is the force from Q2 onto Q1? And we realize that because Q1 and Q2 are positive, there should be a repulsive force along the line joining them, and that is this force F21 on the charge Q1. What is the force from Q3 onto Q1? And we realize that unlike F21, which is a repulsive force, the force F31 from charge 3 onto charge 1 is in fact an attractive force and acts along the line joining the two charges. What is the force on Q1 due to Q4? The answer is that Q1 and Q4 are again positive charges, and therefore the force acts along the line joining the two charges and is indeed a repulsive one, and that gives us the force F41. What is the net force on the charge Q1? That's very simple. Forces are vectors, and so we should add them up vectorially as shown out here. So the net force is in fact the vector sum of each of the three individual forces that we identified, and it is actually given by F1 vector, which is shown to you in this diagram. So with this, let's go ahead and practice our notion of a superposition principle by essentially asking you this other thought question. In this thought question, we're told that we have two big charges, plus capital Q and minus capital Q, that are located at two of the vertices of an equilateral triangle. And at the third vertex of this equilateral triangle, we have a charge little plus Q. Our job is to essentially find the force on the top charge. That's the gist of this thought question. And we realize that because plus big Q and plus little q are basically both positive charges, they should have a repulsive force that acts along the line joining these two charges. That's what we've shown out here. Because minus big Q and plus little q are opposite charges, they should have an attractive force that acts along the line joining the two charges. Therefore, to find the net force on the charge plus little q, we should actually go ahead and do a vector sum of the two vectors that we have drawn. And I will actually remind you that in order to do a vector sum, you have basically to put the two vectors with their tails stuck together and essentially complete the parallelogram like we just did. And the resulting force is the force that is shown to you out here, the resulting vectorial force. And now we see that the resulting force is horizontal and acting to the right, which is in fact why this is the right answer. Okay? So now let's go ahead and do some sort of slightly more quantitative problem, and that is the one shown out here. So we have two charges, Q1 and Q2, both positive, that are separated by a distance of 2 meters. Okay? We have charges Q1 and Q2. In between them, we put a negative charge Q3. The question asked of us in this problem is, what is the location that we should put charge Q3 so that the net force on it is 0? Now notice that when the net force on an object is 0, it is said to be in equilibrium. So we go ahead and say that let Q3 be a distance of x from the origin. Therefore, it will be a distance of 2 minus x from the charge Q1. And it will be a distance of x from the charge Q2. What we want to do is find the right position, x, so that the two forces are exactly balanced. Now, of course, the solution is shown to you out here, but we'll go ahead and roll the solution for you so that we can understand how this works in detail. So in order to find the force F23 between the charge Q2 and Q3, I have to actually go ahead and write K times Q2, now I'm using absolute values, times Q3, divided by the distance between Q2 and Q3, which is just x. So I divide by the distance squared because that's what Coulomb's law tells me to do. In order to achieve force balance, this force F23, which we have just written down, should equal F13, which is the force by charge Q1 on charge Q3, we're about to write that down. So let's go ahead and write that down. That is actually equal to K times absolute value of Q1 times absolute value of Q3 divided by the distance between them, which is actually 2 minus x. And we have to take 2 minus x squared. Okay? Now we can go ahead and do what we always like to do, namely simplify our equations by massive cancellation. So we have k and k canceling off on both sides. We have absolute value of Q3 canceling off on both sides. And we will essentially use the cross product rule to say that we have absolute value of Q2. In fact, Q2 is positive, so putting the absolute value is almost immaterial at this point, times 2 minus x squared is equal to absolute value of Q1, again it's positive, so the absolute value sign is immaterial for this instance, times x squared. Notice that Q2 and Q1 are just numbers. You put them in, and what you have for the solution for x is essentially a quadratic equation, and you go ahead and solve for that quadratic equation and get your answer. So that's the quantitative part of this problem. We'll not go ahead and solve a quadratic equation because that's a skill that you completed in high school. We don't have to repeat it here. But now let's go ahead and answer the intuitive part of this question that is shown below, which is that is this charge in the middle, the charge Q3, is it stable or is it an unstable equilibrium? Now, what does it mean for something to be in a stable or unstable equilibrium? Say you're sitting on a mobile chair, and you tip the chair backwards or forwards by just a little bit. Now, happily, the chair is in stable equilibrium because it basically tips back to its original location. You do not fall down just because you tip a chair by a little bit. All chairs are designed so that they're fundamentally stable so that human beings don't fall off of them. So to get the notion of stability, what we realize is that if you tip something over or push something over to one side, it should want to come back to its original location, and that is the notion of stability. To get a notion of instability, go ahead and take a pencil and try to balance it on your finger with the pencil tip touching your finger. You will find that it's well nigh impossible to balance a pencil that way. And that is mainly because the pencil is in an unstable equilibrium. So if it tips over to one side, there are other forces and torques acting on it which want to make it tip over even more. So the question is, how are we going to assess whether the charge Q3 is in stable equilibrium or unstable equilibrium? The answer is, let's go ahead and take Q3 and move it, scoot it a little bit to the left, and see what happens. What happens is, because Q3 is negative and Q2 is positive, it will have an even larger attractive force F23 pulling it towards Q2. On the other hand, the force F13 will become smaller between Q3 and Q1, and as a result, you will have a runaway situation where F23 will keep pulling it more and more to the left, and Q3 will go to the left. You can do a similar exercise by trying to send Q3 to the right, and you will see that you again have a runaway situation. Now imagine a situation where Q2 is positive, Q1 is positive, and Q3 were instead positive charge. Okay? What would happen in that case? If Q3 moves further towards Q2, then the repulsive forces between Q2 and Q3 become larger, pushing it back to its original location. If Q3 moves more towards Q1, then the repulsive forces between Q3 and Q1 become larger and push it back to its original location. So because Q3 in our problem is negative, it's in a state of equilibrium. However, that equilibrium is indeed an unstable equilibrium. On the other hand, if Q3 were positive, then as long as it's constrained to move only along the x-axis, it would be in a state of stable equilibrium. In other words, any push left or right would cause it to basically regain its original location without going runaway to the left or to the right. So that explains to us the notion of equilibrium. Now let's go ahead and go to the last part of this problem, last part of this section, which deals with this configuration out here. So we have essentially two charges with a charge Q and a mass M. So these are equal charges and equal masses, and they're connected via strings to this pivot point out here. Now, anytime you have a string, you think about tensional forces. So indeed, you have tensional forces which are pulling the two masses, but you also have electric forces that are pushing the two charges away because they have the same charge. So our job in this problem consists of saying that if these two charges are going to be separated from each other by angle theta, one to the right and one to the left, then how does a knowledge of that angle theta allow us to deduce the amount of charge that is on each of these charges? As always with such problems, we want to essentially work out a force law, and let's go ahead and do this in real time with this transparency. So on this transparency, we have the same figure that is shown to us, that was shown to us. We realize that this distance A is actually equal to, so we have A over L is equal to sine theta, therefore A is equal to L sine theta. Okay, always in a physics problem, we like to go ahead and sort out as much geometrical information as we can. So we have A is equal to L sine theta, and we can say that these electric forces F sub E are essentially given to us, and the force F sub E is just equal to K, the Coulomb's constant, times Q, because these are both positive charges, equal charges, so we have Q squared, divided by the distance between them, which is actually equal to 2A, and we have to take that distance and square it. So this gives us the electric force between these two charges. Now there are other forces in play. So each of these objects has a mass m, and therefore each of them has a downward gravitational force given by mg and mg out here. And always, as usual, if there's a string, then there's some sort of tensional force in the string, so we'll call that T. And because these objects are in static equilibrium, the net force on them must be equal to 0. Now notice that I can do a little geometrical construction and deduce that this angle is also theta. And therefore, if I ask what is the vertical component of this tensional force, that vertical component of the tensional force is actually given to me as T times cos theta. And the horizontal part of this tensional force is given to me as T times sine theta. Okay, so we have a rich diagram that we've drawn, and now let's translate that diagram into equations. So for vertical force balance, I have T cos theta is equal to mg. For horizontal force balance, I have T sine theta is equal to Fe. Now, what do you do in such a situation? The answer is that in most physics problems, the tension is not such a major point of interest. And so what you do is you essentially take a ratio. So you obtain T over T times sine theta divided by t times cos theta is equal to Fe divided by mg. So t and t cancels, and we obtain Fe is equal to mg sine theta over cos theta is tan theta. Okay? This is already getting reasonably warm. Now what we do is we go ahead and substitute for Fe. So we obtain k times q squared divided by 2a squared is equal to mg tan theta. And our job is to basically take the angle theta, which is easily observable, and deduce from it the amount of charge that is needed to produce that separation of angles. So we can actually go ahead and do that by realizing that q squared is essentially equal to mg tan theta times 2a squared divided by k. So we have mg times 2a squared divided by k times tan theta. And now we're down to the home stretch because we just use our geometrical representation and stick it in here. So we obtain q squared is equal to mg, and for 2a, instead of 2a, we put 2l sine theta, the whole thing squared, divided by k, and we have tan theta multiplying through. Okay, so if we want q per se, all we have to do is pull out our eraser, erase off the square in front of q, and take square root of this guy, and that's our answer. We're home free. So with that, we have happily completed our first lecture. It's available to you. Please use it to essentially sharpen your knowledge of the subject, and I look forward to having many students in my class who've mastered physics. So with that, I will thank you all, and I will see you all in the next video.